Okay, well, here's another example of a tree, and this is a package that's used more commonly. It's the package rpart, which is recursive partitioning. Recursive partitioning. And the main function in rpart is also called the rpart function, rpart. But it's different from ctree. Ctree stops when it triggers when there's no more improvement in the classification. Ctree it just stops on its own when it's not additionally improving its errorless predictions. rpart, on the other hand, will build out the entire bushy tree. It'll go down and make as many splits, unless you limit the splits. It'll keep on going until there's nothing left to classify, going through every single variable. That's the first step. And then the second step is you prune it back. You manually assess where the error rate, where the improvement in the error rate, or where the decrease in the error rate is minimized. Once your improvement in the error rate starts to turn up again, it stops when you prune it. So it's two-step. Build a very bushy tree, as bushy as you have variables and or things to classify, and then when you run out of that space, then you prune it. And rpart, recursive partitioning, is generally regarded to be it's regarded to be better because it does take the relative degradation of the improvement in error, if that's the way to say it. When your error rate is no longer getting better and better, it stops with the second step, with the pruning. So you grow a tree, prune it back. And it does this because it's got a lot of arguments in the rpart function. There's some good examples in that additional HSAR2 documentation I gave you. But all of these algorithms, all of these functions, when you say algorithm, you're talking about a different function. They have differences. A major one is, what is the splitting covariate? Here with Iris, the first, even though we just threw all four variables at it, it picked petal length first to split. Why? Well, we mentioned that because it through brute force, it figured out the petal length had the most discriminating power, made the purest classification sets on each side of the first split. And it does that through brute force. It does that with every single variable. Okay, but some of them don't. Some of them will limit the number of variables it considers. And if you have 15 variables, it will just look at 5 through some heuristic or some other approach, so as not to be so labor intensive, so computer intensive. And so they differ on that way. They also differ on how the split point is estimated. They also differ on the stopping criterion. So there's some minor differences in how the trees get built with these different functions. And there are demos in rpart, but we're not going to look at that. And there are two basic stop criterions. One is just simply the reduction in error using some mean squared error, reduction in error. A second one is Gini, the decrease in the Gini index. And Gini, I've been reading up on it. I don't completely have it yet, but I will. Gini actually was a criterion developed a couple of centuries ago looking at the purity of different population samples. And it maps into, it's related to the purity of the classifications on both sides of the split, but it's not a pure numeric error measure. It's more related to the shapes of the curves. And I'm going to send out some information before the next class begins on Tuesday about just what Gini is. But Gini is used more often as the stop criterion. The mean decrease in Gini is where it stops, when Gini doesn't get better. And Gini is kind of a mix between reduction and misclassification, also the shape of the misclassification curve. Okay, so we do a set seed here, and we use MBoost. So I already have it installed. We're going to use MBoost just to get the body fat data. We don't need it for the functions. The functions are in RPart. So we load up, and you see all this stuff here. Loads all these other ones. The function RPart is in RPart, so we definitely need to have that library available. And then we call up body fat, and let's take a look. So body fat, it's a data frame, looks like this. Here's the target variable, and what we're doing, these are females. We're predicting fat index, how much fat. Females, dex fat. Everything's numeric. We're using every variable except the first one. So essentially it's a regression task. But RPart can handle both classification and regression. But this is regression. All these other anthropomorphological measurements are also, the variable values are all numeric. So if we say what is the class of our target variable, it's numeric. If we say, well, let's look at the body fat data frame, it has 71 rows and 10 variables. We see that. And attribute is not the same as dimension. Attribute lists out the column headers, these are the column headers, the row headers are the row names, and the class of the object. And so now we're going to split this into training and test, just like we did last time, 70-30, using sample. And once we do that, we're going to set the seed just for the benefit of the sample function. So it will, every time you do this, you'll get the same 70 records if you set the same seed. If you use 1, 2, 3, 4 as a seed, you get the same 70% and the same 30% records. And then we put the 70% into train and the 30% into test. Okay, and we do the same drill we did last time. This time, though, we have more variables. Well, we're using only 5, actually. Age, waist circumference, hip circumference, elbow breadth, and knee breadth to predict fat. So we put all of that into the formula, and then we just run RPart against the formula. But notice this function, this argument, control min split is 10. I have to look each one of these up, but control, here, let's do this. Let's look up RPart. RPart has an argument called control. But if you look at the description, interpretation, it's a list of options. And you get to that here, where you can control the min split, the min bucket, the complexity, and min split is the minimum number of observations that must exist in a node in order for a split to be attempted. And I always get this one confused. So if min split is 10, it does not mean the tree should have 10 splits. It means that the tree should not split unless at a splitting point there will be at least 10 observations on each side. So it's kind of a misname. Min split 10, you think, well, that means the tree should split 10 times. It doesn't. Min bucket, minimum number of observations in any leaf node. CP is a complexity parameter, and so you can what this does, what the control argument in rpart does, because rpart is designed to grow the bushiest tree possible, you might want to limit, you might want to constrain that. And for example, if you have 20 variables, you might want to limit, you might want to put constraints. You don't want the bushiest tree. And that's what you can control or affect with the control variable in rpart. So let's do this again, and we get the formula, and we get the we run the function and put the results in bodyfat rpart, and then we look at the attributes. And the attributes are a little different. Note, these are the attributes of the outputted object. And the outputted object, the fitted tree, it's just one tree, it's the bushy tree, has all of these things. Okay? So this is a more complex function in terms of the output. And what you want to do, you want to prune it back to the point at which the minimum error is not improving. Or said a different way, if you look at this one, it's the X error. The X error is very big, gets a little smaller. With each split, these are, you can consider these different trees. You could say the first tree is just the root node. This is the base split. Then we have two splits, but you could look at this as different trees, even though each of these splits in the same tree. And at some point, the error rate starts to turn up, which is right here, between this one and this one. Just very slightly, but it is. It's starting to turn up. So that tells us that 6 splits, not 7, 6 splits is the best, is the pruned point. You want to prune it back to 6 because you're not, it's not predicting better beyond that. So you might as well stop there. Okay, so this is a more complex algorithm than just the C tree. And so we do that. We there's the CP table. That's what we're looking at. Now we can plot this. We can plot this bushy tree, and it does it in two parts. First of all, you say plot. It just draws all the graphics, and then text actually adds the variables and their division, their split points. And there's some, it gives you the numbers, it's cutting it off a little bit, but n equals 6, and all the leaves, it gives you the numbers.